All right, so in this example, 2.7, we have the same problem as a two-stage problem, but this is now an scenario variable formulation. Okay, so that means that the variables are related to the number of scenarios, not to the number of nodes in the tree. Okay, so again, we're minimizing a cost function over here. Remember that our variables are all in the megawatt units. Okay, so those are power units. And let's say the first term. The first term corresponds to the first scenario, right? It has a probability of 0.2 times the number of hours, right? In a week, right? This is the cost for the contract, right? Which is $45 per megawatt hour. And this is the variable in megawatts, okay? Same here, this is the price of the electricity in scenario number one, $50 per megawatt hour. This is the variable P1 for the scenario one. Okay. Similar, the second term for the scenario number two, and similar for the scenario number three in the third term. Constraints, same as previous example. We have the power that we buy from the contract plus the power that we buy from the pool in scenario one has to be greater than the demand. Okay. Similar for the scenario two and for the scenario three. Notice the difference that now we have one variable for each, for the contract for each scenario, P1C, P1, P2C, P3C. Okay. Because we are analyzing variables in terms of the scenarios, not on the nodes. In the fourth constraint, we have the upper and lower bound for the power that we can buy from the contract, 90 and 0. This is the non-negativity constraint for the powers in each of the scenarios. And last constraint is the non-anticipativity constraint. Okay, that means that the price for the contract has to be the same for all the scenarios. If not, then we have a problem. Okay, the problem, as the author says, is that if those variables are not the same, then the optimization problem is using the information of the uncertainty to define the values of these three variables. Okay. In other words, remember that the contract, right, does not know the realization of the uncertainty. Okay, because that's the first node on the tree, is the root node. So it doesn't have any information about the future. Okay, so setting these three variables to be equal to each one, we are dismissing the possibility that we are using information from the future to take the decision. Okay, so let's see this tree, right? At this particular time step, we don't know what's the uncertainty. The uncertainty is represented by each of these branches. Okay, but at this time step, we don't know what's the realization. Okay, which of these three is going to happen, right? So when we set those three variables equal to each other, we are eliminating the possibility that the optimization problem tries to use the future information to define the value of these three variables over here. Okay. All right. Now let's switch to the code. And I have the code over here. Let me share my screen. So again, we're going to use Notebook, Python, and Gurobi. The data is the same as in the previous example. We create a model. We define the variables. In this case, the variable PC, I am indexing it by the scenarios, which are 1, 2, 3, similar for the power of each of the scenarios, 1, 2, 3, right? So in total, we have 6 variables. Notice that that's a difference with respect to the previous example, because in the previous example, we only have 4 variables. Here we have 6 variables. So we're increasing the complexity of the problem. So then we update the model, right? We set the objective, right? The objective is the first term, right? Okay, so the objective is the number of hours per week, that's 168. And then I am doing a quick sum, right? The probability for each of the scenarios times the sum of the cost of PC for the corresponding scenario and the price of PI for the corresponding scenario. Okay. So if you go back to the example, this is for the first time, this could be 168.2, right? Times 45 of PC1 plus 50 of P1. Okay. So I'm doing a quick sum. This will add up for the other two scenarios as similar terms. Okay. So we are minimizing this objective function. Then we have the constraint. So the constraint is similar as the example 2.6. Okay. But now the PC, I am indexing it for each of the scenarios because we have PC1, PC2, PC3. Okay. So this is PC1 plus P1 has to be greater or equal than the demand in scenario 1, which is 110. Okay. And I'm doing that for all the scenarios. Okay, so those are the three constraints that you see at the beginning of the set of constraints in the problem. And finally, this is the non-anticipativity constraint, right? I'm setting that all the prices of the contract for each of the scenarios, for all of the scenarios, has to be equal between each other. Okay, something I forgot is that in the definition of the variable for PC, I'm including the lower bound and the upper bound, which is 0 and 90 respectively, because that's the amount of power we can buy from the contract. And here I'm including the lower bound of 0. That's the non-negativity constraint for the variable PI. Finally, I update the model, okay, and optimize it. And this is the value of the cost function, okay? Using this visualization code, I'm just showing what's the value. So the pool is 30 and 80 for the first scenario, 20 and 80 for the second scenario, and 0 and 80 for the third scenario. Okay, so that's the example 2.7.